I'm happy to be talking about joint work with Ankur Moitra on algorithmic foundations for the diffraction limit. Now, the subject of this work is a bit further afield from your standard STOC Fox fair. So I want to spend some time on basic science background, both to introduce the relevant concepts, but also to convince you that this is a problem that fits squarely within the wheelhouse of techniques for TTS. Let's start with classical optics 101. If you point a telescope into the night sky, under ideal conditions, you might see something like this. This is a binary star called the Izar, and you'll notice a distinctive ring pattern around one of the stars. It turns out this pattern is neither a feature of this particular star system, nor the result of some imperfection in the telescope's lens. In fact, in a much more controlled setting, if you passed a red laser beam through a small pinhole aperture, you'd see the very same effect, just much clearer. This ring pattern is really the result of a well-studied phenomenon called Fraunhofer diffraction. At a high level, we have some faraway point source of light emanating light waves. That's the yellow circle on the left. And once they hit the circular aperture in the middle, spherical wavefronts are going to emanate from different points on this circular aperture. But they're all going to be off from each other by some phase factor. And the interference that results from these differences in phase factors leads to the characteristic ring pattern that we see in the observation plane on the far right. The image that we get out of this single point source is what we call an airy disk. Okay. So we can think of this airy disk as a pattern, but we can more fruitfully think of it as some kind of probability distribution in the real plane. Specifically, this probability distribution is going to have density function given by I of r comma theta. Here, r and theta are polar coordinates for a point in R2. And you can interpret it as the infinitesimal probability that a photon is going to strike the observation plane at the point given by polar coordinates r comma theta. So this density function takes some unpacking. First, let's start with the parameter sigma. And you can think of this as the analog of the standard deviation for a Gaussian. The spread parameter sigma is going to depend on sort of system-specific constants. So it's going to be proportional to the wavelength of the light being imaged and inversely proportional to the radius of this circular aperture. Now, this function j sub 1 is just the Bessel function of the first kind. This won't be super important to us. The main takeaway should be that this quantity inside of the square is proportional to the Fourier transform of the circular aperture. In particular, it's the 2D Fourier transform of the indicator function of an origin-centered ball with the radius that depends on the spread parameter sigma. You can ask, why is there a square in front of this in this function? And the reason is that we're really looking at the magnitude of the electric field at the observation plane. Remarkably, this distribution was discovered by Sir George Beidel-Airy sometime in the mid-1800s and remains one of the fundamental objects in sort of classical Fourier optics. Okay? And this is going to be the central object for the rest of our talk. Okay. So a natural question to ask is, if I take multiple point sources and they're all really close by, well, this airy disk introduces some level of blurring. Does that make it harder to distinguish distinct point sources? Okay, so let's say I have two different point sources and I'm moving them closer together. At some point, they're going to be close enough that it appears like the airy disk pattern I'm getting is just coming from a single point source. And indeed, the conventional wisdom is that this is just some fundamental limitation that diffraction places on how well an optical system can resolve distinct objects. And the natural question to ask is, what is this critical threshold below which it actually becomes impossible to resolve? Namely, what is the level of separation at which resolution becomes impossible? This is an age-old question that dates back to foundational work of Airy and also physicists like Lord Rayleigh. So there's a well-known rule of thumb called the Rayleigh criterion that says that as soon as the center of one of the airy disks intersects the first ring of the other airy disk, it becomes impossible to resolve. And you can work this out, and this amounts to roughly a separation of 1.22 pi times the spread parameter sigma. There have been plenty of other criteria proposed. There's also the Sparrow limit. And this says that as soon as the mixture of the two area disks, PDF, becomes unimodal, then resolution becomes impossible. And this amounts to roughly 0.94 pi sigma separation. Perhaps one of the most well-known sort of criteria for dictating, the separation below which resolution is impossible is the so-called Abbe limit. So the definition of this is a bit more technical, but at a high level, it's dictated by the Fourier transform of the area disk itself. Okay. So remember the quantity inside of the square in the definition of the area density function was the Fourier transform of the aperture. And so the Fourier transform of the square of the Fourier transform of the aperture is just going to be the convolution of the aperture with itself. Okay, and this is going to be some function which eventually goes to zero as soon as the two copies of the aperture are disjoint. Okay, so it's this function that I've plotted over here. Particularly, this function is supported on a radius of pi sigma inverse. And so the Abbe limit corresponds to a separation of pi sigma between the two centers. This is a very well-known sort of limit with a formal description in one dimension, but it's just as often used as a heuristic for dictating diffraction limits in two dimensions. And you can even see it inscribed here on this memorial statue for Ernst Abbe. In fact, in 2014, when the Nobel Prize in Chemistry was awarded to Betzig, Hell, and Moerner for developing super resolution microscopy, which managed to circumvent any reasonable notion of diffraction limits, even in this press release for the Nobel Prize, you can see that they pinpoint the Abbe limit as the de facto diffraction limit for resolution by classical optical systems. Okay, but at this point, the picture is a bit muddy. I've told you three different constant factors that have been proposed as sort of rigorous or semi-rigorous definitions for the diffraction limit. And in fact, there are plenty more that were proposed in the decades since Abbe and Lord Rayleigh. And so a natural question to ask is, which of these criteria is the right one, if any? In particular, is the diffraction limit simply a useful heuristic, or is there some formal interpretation that we can impose upon this quantity? Now, this isn't just some TCS style question that one can ask about the setup. This is a question that's dated back to even the early 1900s. So, for instance, Sir Arthur Schuster questioned the validity of the Rayleigh criterion by pointing out that the motivation for defining it as the point at which one ring intersects the other area disk was largely motivated by physiological reasons. That as soon as we reach this critical distance, the naked eye, looking through a telescope, it becomes difficult to resolve two distinct point sources. Okay. On the other hand, Richard Feynman points out that if we had infinite exposure times and could make sufficiently careful measurements, then in principle, if I have a mixture of two different area disks of truly distinct point sources, the resulting image that they form has to be different from the image formed by just a single area disk. At least in the infinite sample limit, it appears that the density function for a convex combination of two area disks must be different from that of a single area disk. And decades later, Joseph Goodman points out that any criterion that fails to take into account any notion of signal to noise ratio that comes from things like shot noise from finite exposure times must be a subjective notion of diffraction limit. Okay, so again, it's not just us asking this, but really a long-standing debate in the physics community of whether diffraction limit for classical optical systems has any kind of rigorous meaning. Okay, and that's going to be the question that we're going to tackle in this work. So now let me turn to what we actually show. And to put things into context, I want to spend a bit of time motivating the results from the standpoint of a topic that should be more familiar to this audience, which is mixture model learning. So if I give you some image that consists of photons sampled from a bunch of different area disks, this is something that I would see in a microscope or a telescope. And my goal is to figure out the locations of the different point sources the centers of these area disks on the observation plane. If you think about this, is nothing more than trying to learn the parameters of a mixture model given random samples from that mixture model. Okay, so for those who might not be familiar with mixture model learning, here's a way to formally state this problem. So I'll call the following generative model a mixture of k area disks. We have as unknown parameters the intensities of the different area disks in my mixture. And these are parametrized by a vector lambda1 to lambda k, whose entries sum up to 1. The vector in the simplex. And of course, the main parameters of interest are the centers of these different area disks. And these are just points mu1 to mu k in R2. To sample from this probability distribution, I'm going to select some index I from 1 to k with probability equal to the corresponding intensity, lambda sub I. And then I'm going to sample from the ith area disk, namely the one centered at mu sub I. Okay, so this is a mixture model. And indeed, if you replaced this last bit about area disk centered at mu I with just a standard Gaussian centered at mu sub I, then this distribution would simply be a mixture of spherical Gaussians. Okay, so that's the starting point for the connection to TCFs. And indeed, there's been a ton of work in theoretical computer science on the problem of learning mixtures of Gaussians. We have efficient algorithms for learning mixtures of a constant number of arbitrary Gaussians, even ones that aren't spherical. And our main sort of quantity of interest is really the level of separation between the different components. So let's define separation delta to be the minimum pairwise distance between any two distinct centers in the mixture. Okay. So if we focus on the separation parameter, then we can pinpoint a particular threshold, at least in an asymptotic sense. So that below this threshold of root log k, you can prove that you need super polynomial number of samples to learn. But above this threshold, polynomially many samples suffice. Okay, and this is a result of Rega Vijayaraghavan, for which the upper bound was refined by Kwan and Karamanis. Okay, so this is sort of the state of the art for learning mixtures of Gaussians. And the results that we are going to show for learning mixtures of area disks are really going to be analogous in spirit, although the techniques, as we'll see, will be quite different. Okay, so the first result we show will be completely analogous to bullet point 1. For a constant number of area disks, we essentially show that diffraction imposes no fundamental limitation to resolution. Basically, we show that given samples from, say, a delta separated mixture of k area disks, where each relative intensity is at least lambda, there's an algorithm that takes a polynomial number of samples in all of these parameters except for k, and learns all of the parameters of the mixture of area disks to error epsilon in an L2 sense. Okay, so the main point is that this thing is unfortunately exponential in k, but as long as k is O of 1, we're fine. This is going to be a polynomial time algorithm with polynomial sample complexity. Okay, so that was the analog to the first kind of sort of mixture model, the first flavor of mixture model learning results. Namely, when I have a bounded number of components to my mixture, I can learn in polynomial time, regardless of the level of separation. On the other hand, if I have a super constant number of components, what we show is that actually the diffraction limit manifests as a statistical phase transition in the following sense. So remember, for mixtures of Gaussians, there was this critical threshold, root log k, which was pinpointed up to constant factors, or at least in an asymptotic sense, where if your separation was little omega versus little o, you got a significantly different statistical behavior. So here we give it an even more refined picture in the case of area disks, and we show that there is actually just a hard constant, which we pinpoint within constant factors for the separation, such that below this level of separation, if the mixture of area disks is too tightly packed, then it's going to be hard to learn in the sense that you'll need an exponential number of samples. And above this level of separation, if the area disks are sufficiently spaced out, we actually give a different algorithm which has time and sample complexity, which is polynomial in all parameters. Not just in 1 over error, 1 over relative intensity, et cetera, but also polynomial in the number of area disks. Okay, so as long as you have a polynomial number of area disks, we get a polynomial time algorithm. Okay, so this really is the rigorous answer for what does it mean for there to be a diffraction limit. We show that in any reasonable physical setup where you're constrained by the number of samples you can take or the number of photons that you can collect, for instance, if you have finite exposure time, there really is a fundamental limit imposed by diffraction, but it only manifests when you think of a large number of area disks. And actually, the most interesting part of this result, in my opinion, is that this statistical phase transition that we pinpoint provably does not coincide with the Abbe limit. Okay, so remember, the Abbe limit occurred at separation roughly pi times sigma. What we're saying is that the phase transition occurs somewhere between 1.15 and 1.53 pi sigma. One last interpretation you can take for this result is that this gives a theoretical justification for something you observe in practice, namely that there are settings where, for instance, in astronomy, if you have few point sources, then it seems like classical optical systems can actually go well below the diffraction limit, as predicted by people like Schuster, Feynman, and Goodman. And in settings where you have many point sources, for instance, if you're imaging a live cell in microscopy, then classical optical systems sort of hit a wall, and you really need genuinely new imaging technologies to achieve super resolution. Okay, and this is really the subject of this Nobel Prize in chemistry. Okay, so that's all I wanted to say about the results. At this point, I want to turn to the techniques. I won't be able to go too much in detail into the algorithms themselves, but I want to give you a flavor for the kinds of analysis questions that arise when dealing with these algorithms. Okay, so first let me tell you a very simple standard reduction to a related question. So at a high level, we'd like to take all of these points which have been convolved with this Airy function, and we'd like to somehow remove the blur that comes from the Airy function and just get the points themselves. So we'd like to do some kind of deconvolution. So here's the density function for a mixture of k Airy disks. And you can easily write down the Fourier transform of this density as follows. Okay, so remember, we start with a density which is given by a convolution. The Fourier transform is simply going to be a multiplication between the Fourier transform of the kernel that we're convolving by and the Fourier transform of the collection of points. Okay, so this I hat W is, or this I hat omega is precisely the Fourier transform of the kernel, which is given by the Airy disk. And remember, this is, this function is some radially symmetric function whose univariate definition is given by this plot here. And in particular, this sum in yellow is an exponential sum that corresponds to the Fourier transform of the convex combination of points. So the key takeaway is that for any omega, which is in the support of I hat, so any omega whose norm is at most pi sigma inverse, you can recover an estimate for this exponential sum by simply estimating f hat omega from samples and dividing by I hat omega, which we know exactly. We have an analytic form for this I hat omega. So this gives a reduction to the following related question of sparse Fourier transform off the grid. So for all of the algorithms in our work, we equivalently give an algorithm for the following problem and obtain an algorithm for the original problem via the aforementioned reduction. So here's the problem that we give an algorithm for. We assume noisy query access to the following function, which takes omega to this exponential sum here. And we have query access for any omega, which has norm at most pi sigma inverse. And our goal is to recover estimates for all the relevant parameters, namely the intensities lambda I and the centers mu sub I. So it's really about getting an algorithm for this particular question. And in the regime where we have a constant number of disks, our technique is simply to appeal to existing algorithms for the univariate case. Okay? So we've shown in previous work that in the univariate case, we essentially have an optimal algorithm that's based on something called the matrix pencil method. So the idea will simply be to take our 2D setting and take random projections of our data points and use the matrix pencil method to compute the projections of the centers along these random directions, and then simply piece together these one-dimensional estimates to get a full two-dimensional estimate. Okay, so to an audience that's familiar with mixture model learning, this algorithmic result is perhaps the least surprising of the results I'll tell you about. But let me now turn to the well-separated case. So if the level of separation is at least this critical 1.53 pi sigma, then we use a different approach that was originally introduced by Huang and Kakide based on tensor decomposition. So I won't go into the details of the algorithm, but to give you a flavor for how to analyze this algorithm, let me tell you about a very clean Fourier analytic question, which is at the heart of the analysis. So this is just a question about cancellations in exponential sums. The question is, what is the smallest level of separation delta for which the following integral inequality holds for all vectors lambda and rk and all delta separated collections of centers mu sub j? Right, so on the left-hand side, we have an integral of this exponential sum that I showed in previous slides, absolute value squared, over the unit ball of possible frequencies. And the hope is that you can't come up with a collection of delta separated centers, mu sub j, for which there are too many cancellations. In other words, you can't come up with a collection of centers for which the integrand, this exponential sum, is too close to zero for most of the frequencies omega in the unit ball. Okay? So you can think of this as really lower bounding some minimum singular value of a particular matrix. So really this question is one of establishing some kind of condition number bound. Okay, but this is, in my view, a pretty clean Fourier analytic question. And while we don't pinpoint the exact value of delta, it turns out that by getting reasonable upper and lower bounds, these immediately translate to algorithms and information theoretic lower bounds for learning mixtures of area disks. Okay, so to establish an upper bound on the smallest possible delta, we use an extremal function called the Ball minorant that was introduced by work of Holt and Baller in the mid-90s. And we essentially show that as long as the level of separation is at least this 1.53 threshold, then this condition number bound holds. On the lower bound side, we exhibit a collection of centers which are separated by roughly 1.15, for which this integral inequality fails to hold. And in particular, it failed to hold for a closely related problem, which we then use to establish our information theoretic lower bound. Okay, so that's all I wanted to say about the techniques. I encourage you to check out the full version or to ask me any questions during the poster session. Let me now turn to takeaways and open problems. The main takeaway from this work is, of course, that we give a rigorous formulation of the diffraction limit as a statistical phase transition for a particular inverse problem involving learning a mixture model. Of course, the main technical open question is, what is the right constant factor? We've shown it's somewhere in between 1.15 and 1.53, which in particular rules out famous resolution limits like the Sparrow limit and the Abbe limit. What is the actual right constant factor? And this, I argue, really has to do with understanding the critical delta from the Fourier analytic question from the previous slide. And let me just conclude with sort of a conceptual question, which is, this is a nice instance where using the lens of theoretical computer science turns out to be very fruitful for understanding a particular inverse problem in the sciences. So could there be other problems in sciences, either in optics or in other disciplines, which could be similarly amenable to tools from machine learning theory or TCS more broadly? Okay. So if you have any questions, please feel free to visit me during the poster session. Otherwise, thanks very much for your time, and I hope you enjoyed this talk.